Okay, so in the last lecture we had stopped at the definition as well as the basic equation of AM for a single tone case. Okay, now we shall try to see the time domain representation of it and see what are all the components we get. Okay, so when you try to expand this S of t equation that is written above, that is this equation. Okay, just hold on for a while. So let me use a pen. So if you try to see this equation, and if you expand that equation, what you get is basically, okay, just hold on for a second. Okay, if you see this equation here, yeah, if you see this equation and if you try to expand it, this is the equation what you basically get, where S of t is equal to EC or AC into cos of omega ct plus mu, which is equivalent to m AC into AC by 2 into cos of 2 pi fc plus 2 pi fm into t. Quite interesting. We are able to get something here, plus mu or ma into AC divided by 2 into cos of 2 pi fc minus 2 pi fm into t. So what you observe is there are three components here. Okay, number one is this fellow, number two is this, number three is this. What is the frequency of the first component? It is fc, isn't it? Second, it's fc plus fm. Third is fc minus fm. So fc is anyways the carrier. The other two components what you see, which is fc plus fm and fc minus fm, they are called the upper sideband and the lower sideband frequency components. And this is what you observe when you try to perform a amplitude modulation. So you will get two different components apart from the carrier. So in total there will be three components in a amplitude modulated wave. Okay. Okay, so now we shall see what is the frequency domain representation of this. Okay, so when I try to take the Fourier transformation of this signal, S of t equals AC cos 2 pi fct whole multiplied by 1 plus ma into cos 2 pi fmt, I get this equation. Okay, and what is that equation? The equation is right in front of you here. Fine. Okay, so which is AC by 2 into delta of f minus fc plus delta of f plus fc, because cos 2 pi fct delta, Fourier transformation is delta of f minus fc and delta of f plus fc divided by 2. Okay, that's basically the Fourier transformation of a cos, and sign will be, you will have a complex for the second term with a negative sign. Okay, so when you expand it, this is what you get. So what you will have is a component of delta with a frequency fc or at a frequency fc, and AC MA divided by 2 into M of F minus FC plus M of F plus FC. So M basically stands for the modulating signal spectrum, M of F minus FC, but it's a shifted version of M of F, shifted by an amount of FC to the right, shifted by an amount of FC to the left. And what you observe is this kind of frequency response. Where is it? Right here. So this is what you basically get. Okay, so this is how will the frequency response of an amplitude modulated wave will look like. So this is case of a a multi-tone signal. If you take a single tone signal, the spectrum will look like this. So let me write it this way. Okay, so what you will have is this kind of spectrum. So this center frequency will be FC, this will be FC plus FM, this will be FC minus FM, and you will also have frequency components which are mirror images in the negative axis of frequency, which will not have any significance, but the Fourier makes us to write all those components. Okay, so the Fourier transformation equation is going to look like this, and we also got to know how the spectrum will look like when you take a single tone signal, modulating signal. Okay, so this is how the frequency domain representation looks like. So further to it, we can go ahead with the definition of modulation index in a much more detailed way. Okay, so when you have a multi-tone signal, it may look more complex than a single tone. The waveform that we saw here is for a single tone case. So this waveform what we've written is a single tone case waveform. So how will this waveform that we wrote here, where is it? Yeah. So this waveform is basically for a single tone case. If you see the envelope, that's a sine wave. So when you have a complex signal, the waveform may look maybe something like this. And you can see the carrier wave filled in within this. So the envelope is no more a sine wave, even though it is looking like a sine, but it will not be a sine wave because it's a combination of many tones as such. So it will become a complex signal for us. So in such cases, how do you basically define what is called a modulation index, or it's also called the depth of the modulation. Okay, that is defined as A max minus A min divided by A max plus A min. Let me tell you what is the meaning of A max and A min here. Okay, so when you consider a multi-tone, maybe it may look like this. Just for example, I'm writing it, and you can see the amplitudes of the carrier getting varied in accordance with the amplitude of the modulating signal. So A max is basically this part. And what is A min? If you try to see what is the minimum voltage value, this becomes the minimum voltage value. So this is A max and that is A min. So you have to find those two values and try to find what is modulation index. Okay, that is how you do it. So based on this modulation index, or which is also called the depth of modulation, okay, so we can define three different varieties of amplitude modulation. Number one, under modulation, if the value of MA is lesser than 1, and critical modulation if the value of MA is equal to 1, and over modulation if the value of MA is greater than 1. So this is what you get as. We'll see how the waveform will look like now. If you see the waveform, these are the three waveforms that we have written for three different cases. And can somebody tell me in which case you see the envelope getting retained without any sort of distortion in the envelope? Obviously it is in the first case, because if you see the critical and over modulation, you can observe this part of the wave. Okay, just a second. You can observe this part of the wave. Yeah, this part of the wave is all kind of distorted. But in case of under modulation, the wave shape is retained as it is. So that is when we say that under modulation is always good for the reproduction of the signal back at the receiver side. So we always perform under modulation. That's the meaning of this. So moving on to the next one. What are the two different methods of generation of AM? So we have gotten to know what is the definition of amplitude modulation and how the waveform will look like, what is the time domain, what is the frequency domain representation, and we also understood the definition of modulation index and how is it going to affect the different varieties of AM, like under, critical, and over modulation. So that MA value will affect the type of modulation, AM modulation we do. So after this, we have to understand how we can generate it practically. So there are two, methods of generation. One is called a square law modulator. Other one is called a switching modulator. In both these cases, we use basically a non-linear device, which will be a kind of diode. Okay. So, so this is the basically the, the circuit diagram of a non-linear device, and the band pass filter connection, which is basically a square law modulator. So if we have to basically understand the operation of this, if you have to understand the basic operation of this, we'll have to write few equations of a non-linear device. We'll see what is it. Okay, and probably we have that equation here. If you can observe, this is the equation of the non-linear device right here. This is basically the equation of the non-linear device. So this is the equation that we have got for the nonlinear device. So we'll have to substitute for V1 of t and try to expand it and eliminate all other higher frequency components. So this further, if you try to write it, what you will get is an equation like this. So this is the output of the bandpass filter, which is equivalent to your amplitude modulation. Okay, in the next video, we'll see switching modulator.